What if I told you that right now, you're racing through the universe at 500,000 miles per hour, spinning on a planet that's orbiting a star, which itself is hurtling around a supermassive black hole at the heart of a galaxy so vast, it would take light 2 million years to cross it. You can't feel it, you can't see it. But every second, you're part of a cosmic journey more incredible than any science fiction story. And thanks to the latest discoveries from the James Webb Space Telescope, everything we thought we knew about our galaxy is being rewritten, revealing secrets, dangers, and wonders that will change the way you see the night sky forever. If you're fascinated by the mysteries of our universe and want to join me as we uncover the hidden truths of the cosmos, make sure to hit that subscribe button and turn on notifications. Your support helps us explore deeper, ask bigger questions, and bring the wonders of the Milky Way right to you. Don't miss what's coming next. Subscribe now and be part of this cosmic adventure. At this very moment, you are racing through the cosmos at a speed that defies imagination, over 500,000 miles per hour. You don't sense it, you can't see it, yet every instant, our entire world is spinning around a gravitational monster at the heart of our galaxy, a black hole millions of times heavier than our own sun. For decades, we thought we had a handle on what that meant. But the latest discoveries, especially those from the James Webb Space Telescope, have upended everything. Astronomers are now confronting a Milky Way that is more immense, more turbulent, and more mysterious than anyone had dared to believe. From sudden bursts of energy erupting from the galactic core to unseen matter stretching far beyond the stars we can observe, the story of our galaxy is being rewritten in real time. If you find this exploration fascinating, your support, liking and subscribing, helps us continue the journey. Now, let's begin. Step outside on a clear night and look up. If you're lucky enough to be far from city lights, you might notice a pale, milky band arching across the sky. That faint glow is what gave our galaxy its name. Ancient cultures imagined it as a trail of spilled milk from the gods, never realizing what they were truly witnessing. Even in recent history, our understanding was limited. For generations, textbooks and documentaries described the Milky Way as a disk about 100,000 light-years wide, a vast spinning collection of stars, dust, and cosmic secrets. But that number, repeated everywhere, was off the mark. New measurements, using data from the Gaia Space Observatory and confirmed by James Webb's observations, have doubled that estimate. The Milky Way's visible disk may actually span closer to 200,000 light-years from one edge to the other. And if you include the invisible shroud of dark matter that envelopes our galaxy, the true diameter could reach nearly 2 million light-years. Imagine that light, the fastest thing in existence, would need 2 million years just to travel from one side of our galactic home to the other. Let that number settle in your mind for a moment. But the surprises don't end there. You are not stationary as you read this. Earth itself spins at about 1,000 miles per hour at the equator. Our planet orbits the Sun at a breakneck 67,000 miles per hour, and the entire solar system is hurtling around the center of the Milky Way at over 500,000 miles per hour. Every person who has ever lived has been a passenger on this cosmic express, racing through space without ever feeling the motion. The galaxy completes a single rotation every 230 million years, a period astronomers call a galactic year. The last time our solar system was in this exact spot, dinosaurs had not yet appeared on Earth. The next time we return, the world will be unrecognizable. For a long time, scientists considered the Milky Way to be a fairly typical spiral galaxy, nothing out of the ordinary. But the James Webb Telescope has revealed that our galaxy is anything but average. Its structure is more unusual than previously thought. The inner disk is flatter than expected, and the distribution of stars doesn't follow the neat patterns astronomers once assumed. Thanks to Webb's ability to see in infrared, we can now peer through the thick clouds of dust that once blocked our view. Regions that were previously invisible are now revealed in intricate detail. Stars that were hidden now shine in complex networks, and structures that existed only in theory are now visible on screens in research centers around the globe. These new images are forcing scientists to redraw their maps. The Milky Way is not just larger than we believed, it's more intricate, more violent, and more dynamic than any previous generation could have imagined. But the sheer size of our galaxy is only the beginning of the story. At the heart of all this swirling chaos lies something so massive it bends the very fabric of space and time. And recent observations have shown that it behaves in ways no one predicted. You are much closer to this cosmic powerhouse than you might think. If someone asked where you live, you might answer with your city, your country, or your continent. But your true address is far stranger. You exist on a small, rocky planet orbiting an ordinary star, which itself is located on the inner edge of a spiral arm known as the Orion Arm, or, as some astronomers call it, the Orion Spur, since it branches off from a larger structure. This is your galactic neighborhood. The Orion Arm sits between two much larger arms. The Sagittarius Arm, which lies closer to the galactic center, and the Perseus Arm, which stretches farther out toward the edge. Our solar system floats in the space between them, like a house on a quiet street between two busy highways. From our position, the center of the galaxy is about 26,000 light-years away. That means the light you see from that direction began its journey 26,000 years ago, when humans were painting animals on cave walls and hunting with stone tools. Most people never consider this. We are not near the center, nor are we at the edge. We're about 2/3 of the way out from the core. This location may be crucial for life as we know it. Closer to the center, stars are packed so tightly that radiation levels soar and supernovas erupt more frequently, making stable planetary orbits and life much less likely. Farther out, there are fewer heavy elements, the building blocks of planets and living things, because those elements are forged in the hearts of dying stars. Worlds forming in the outer galaxy might lack the raw materials needed for complex chemistry. Our position seems almost perfectly balanced. Far enough from the chaos to survive, close enough to the action to have the elements we need. Scientists call this the galactic habitable zone. It's a real concept, though its exact boundaries are still being mapped. James Webb is helping refine that map. By studying star-forming regions throughout the galaxy, astronomers can now track where heavy elements are concentrated, see which zones produce stars capable of hosting rocky planets, and identify danger zones where radiation would destroy any emerging life. What they've found is surprising. The habitable zone might be larger than previously thought, or it may have shifted over billions of years as the galaxy evolved. Our solar system may have migrated from a different location entirely, drifting outward over cosmic time. The galaxy beneath your feet is not static. Stars move, arms rotate, entire regions reshape themselves over millions of years. The neighborhood you call home today looked completely different when our planet formed 4.5 billion years ago. But if the outer reaches feel distant, and the inner zones feel dangerous, what about the very center? What lies at the heart of it all? Something ancient, something powerful, and, according to James Webb, something far more active than anyone expected. Take a moment and count to 10. In that brief span, a beam of light would have traveled nearly 2 million miles. Yet, even at that unimaginable speed, light could not cross more than a tiny fraction of our galaxy in a human lifetime. So, how many stars actually fill the Milky Way? The honest answer is that we don't know the exact number. Estimates range from 100 billion to 400 billion stars. The uncertainty isn't for lack of trying. Counting stars is far more complicated than it sounds. Imagine standing in a packed stadium at night. You can easily count the people nearby, but as you look farther, the crowd blurs together. Bright lights obscure some faces, while shadows hide others. Now, imagine that stadium stretches for thousands of miles in every direction, filled with fog and dazzling spotlights, scattered at random. That's the challenge astronomers face when they try to tally the stars in our galaxy. Dust clouds block visible light from distant regions. The brightest stars outshine their dimmer neighbors. The galactic center is so densely packed that individual stars blend into a continuous haze. And the smallest, faintest stars, red dwarfs, which make up the majority, become invisible beyond a few hundred light years. The James Webb Space Telescope is changing this calculation. Its infrared vision can pierce through dust that blocks visible light. Webb's instruments detect the heat signatures of stars too faint and too distant for previous telescopes to spot. Every new observation adds more data points, gradually filling in the gaps. Here's a thought that might keep you up at night. For every star you can see with your naked eye, about 6,000 on a perfect, dark night, there are millions more hidden behind them. The faint band of the Milky Way that ancient people wondered about contains more individual stars than all the grains of sand on a beach. And each of those stars could host planets. Current estimates suggest the Milky Way contains at least as many planets as stars, possibly more. That means somewhere between 100 billion and 400 billion worlds orbit the stars of our galaxy: rocky planets, gas giants, frozen moons, burning infernos, and perhaps, hidden among them, places where something looks up at their own sky and wonders the same questions we do. This is no longer just speculation. The Kepler mission and ground-based surveys have detected thousands of exoplanets. Statistical analysis extends those findings across the entire galaxy. Planets are not rare, they are everywhere. But here's the twist: the number of stars in our galaxy isn't fixed. New stars are born every year. Old stars die. The population is always shifting. Right now, somewhere in the Milky Way, a cloud of gas is collapsing under its own gravity. Within a few 100,000 years, a new star will ignite. Elsewhere, an ancient star is exhaling its final breath, scattering the elements that will become the next generation of worlds. The Milky Way is not a museum, it's a factory, a furnace, a living engine of creation and destruction. And the most violent part of that engine sits at the center, where something monstrous controls everything around it. Every galaxy has a secret at its core. Ours is called Sagittarius A, pronounced Sagittarius A star, but the name is less important than what it is: a supermassive black hole, 4 million times heavier than our Sun, squeezed into a space smaller than Mercury's orbit, so dense that not even light can escape once it crosses the event horizon. For decades, astronomers suspected something massive lurked at the galactic center. Stars in that region moved too quickly, whipping around an invisible point at speeds that made no sense unless something with enormous gravity anchored them. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A, a glowing ring of superheated gas surrounding a dark shadow. The shadow wasn't the black hole itself, but the absence where light could not escape. That image confirmed what physics had predicted, but James Webb has revealed something the images could not show: behavior, activity, chaos that never stops. Surrounding the black hole is a disk of gas and dust called an accretion disk. Material spirals inward, accelerating as it approaches the point of no return. Friction heats the gas to millions of degrees. As that material falls, it doesn't go quietly, it screams in light. Flares erupt constantly from the disk, Some last only seconds, others blaze for hours. The brightness fluctuates wildly, rising and falling in patterns that seem almost random. Scientists expected some activity. Black holes are messy eaters. Gas doesn't fall smoothly into the void. Turbulence creates bursts and eruptions. But the scale of what Webb observed shocked researchers. 5 or 6 major flares every single day. Dozens of smaller bursts in between. No period of rest. No quiet moments. The black hole at the center of our galaxy is throwing a constant tantrum, firing off cosmic explosions around the clock. One researcher described it as bubbling with activity. Another said it never reaches a steady state. And here's where the mystery deepens. The flares change brightness at different wavelengths of light, but not at the same time. Shorter wavelengths dim slightly before longer wavelengths do. The delays range from a few seconds to nearly a minute. This timing reveals something about the physics happening at the edge of oblivion. Magnetic fields twist and reconnect. Particles accelerate to nearly the speed of light. Energy releases in cascades that ripple outward through the disk. The details remain a theory being tested with every new observation. But one thing is certain, the monster at the center of the Milky Way is far more restless than anyone imagined, and the show it puts on is unlike anything else in the galaxy. What exactly causes these flares? What triggers the explosions? The answer might rewrite our understanding of how black holes feed. Imagine a strobe light in absolute darkness, flashing unpredictably, sometimes bright enough to blind you, sometimes barely a flicker, never stopping, never resting. That's what James Webb witnessed when it stared at the center of our galaxy. Sagittarius A is putting on a light show, and it's been doing so for billions of years, without an audience capable of watching. Until now, James Webb's near-infrared camera spent a total of 48 hours observing the heart of our galaxy, spread across multiple sessions throughout an entire year. This gave astronomers the most extended and detailed look ever at the supermassive void anchoring the Milky Way. What they saw was pure chaos. The accretion disk around the black hole emits infrared radiation as gas heats up during its death spiral. That radiation is anything but steady. In the data, researchers watched the brightness rise and fall like a heartbeat with no regular rhythm. Then, without warning, massive eruptions, brilliant flares, would spike far above the baseline. One moment, the signal showed gentle variation, the next, an explosion of light, then calm again, then another burst. One scientist compared it to watching fireworks from up close. You never know exactly when the next one will explode or how bright it will be. You only know another is coming. The team counted the activity carefully. 5 to 6 large flares erupted every day. Between them, smaller sub-flares flickered in rapid succession. There was no pattern they could identify, no rhythm, no predictable cycle. This randomness itself is a clue. If the flares followed a pattern, it might suggest organized structures in the accretion disk, hotspots orbiting at regular intervals, clumps of material falling in at predictable rates. The lack of pattern points to something more turbulent. Material enters the disk from multiple directions. Magnetic fields tangle and snap. Gas collides with gas in violent shocks. The chaos feeds itself, creating conditions where explosions can happen anywhere, at any time. This is significant for understanding our galaxy. Supermassive black holes are not just gravitational anchors. They shape the galaxies around them. The energy released during feeding episodes can heat gas clouds, preventing new stars from forming. It can also blast material outward, seeding the galaxy with heavy elements. Sagittarius A is relatively quiet compared to the monsters at the centers of some galaxies. Quasars in the distant universe outshine their host galaxies by hundreds of times. Our black hole is more like a simmering pot than a raging inferno. But simmering is not silent. The constant flares Webb detected reveal that even a calm black hole never truly rests. Energy pours out continuously, influencing the environment around it in ways astronomers are only beginning to understand. And the flares carry another secret. The way their brightness changes at different wavelengths tells a story about what happens in the final moments before matter vanishes forever. A story written in light, at the edge of a shadow that swallows everything. Something strange happens at the edge of a black hole. Light bends, time slows, space itself twists into shapes that defy intuition. And now, James Webb has captured evidence of processes so extreme that explaining them pushes physics to its limits. When the telescope observed flares from Sagittarius A, it recorded them at two different wavelengths of infrared light at the same time. This dual view revealed something unexpected. The brightness didn't change at the same moment in both wavelengths. Shorter wavelengths dimmed slightly before longer wavelengths did. The delays varied, sometimes a few seconds, sometimes nearly a minute. But the pattern held. Short wavelengths led, long wavelengths followed. This timing difference is a fingerprint of the physics at work. Astronomers believe two separate mechanisms drive the flares. The large eruptions likely come from magnetic reconnection events. Imagine two magnetic field lines colliding. When they snap and reconnect, they release tremendous energy. Particles accelerate to nearly light speed. Radiation pours out across the spectrum. This process happens around our own sun during solar flares, but around a black hole, the energies are vastly higher. The magnetic fields are stronger. The particles move faster. The explosions are far more violent. The smaller, rapid bursts between major flares might have a different origin. Gas in the accretion disk doesn't flow smoothly. Turbulence creates instabilities. Pockets of material compress suddenly, heating up and releasing light before cooling again. These hotspots would rise and fade quickly, producing the flickering behavior Webb detected. Both mechanisms remain theories supported by the data, but not yet proven definitively. Here's why the wavelength timing matters. When high-energy particles spiral around magnetic field lines, they emit radiation. Higher-energy particles emit shorter, wavelength light. Lower-energy particles emit longer wavelengths. As the particles lose energy over time, the emission shifts from short wavelengths to long. The time delay Webb measured matches this expectation. Particles accelerated during a flare emit short wavelength light first. As they cool, their emission shifts longer. The seconds to minutes of delay reveal how quickly the particles lose energy, and how far they travel around the magnetic field lines before fading. This is physics confirmed by observation. The data narrows down the models of what happens near a black hole. It rules out some theories and supports others. Every flare Webb catches adds another piece to a puzzle that has frustrated physicists for decades. But understanding the physics is not just an academic exercise. These processes have shaped our galaxy. The energy released near Sagittarius A, over billions of years, has influenced star formation, gas dynamics, and the overall structure of the Milky Way. The monster at the center is not just sitting there. It has been sculpting its surroundings since the galaxy was young. And the sculpting continues today in ways we can finally witness. But the black hole is not the only site of cosmic construction. Nearby, one of the most massive clouds in the galaxy is birthing new stars at a furious rate. Just 300 light-years from the supermassive black hole, something magnificent is happening. Stars are being born. The region is called Sagittarius B2. It is the largest and most active star-forming cloud in the entire Milky Way. A massive concentration of gas and dust, so thick that visible light cannot escape. For decades, astronomers knew it existed but could not see inside. James Webb changed that. The telescope's infrared instruments pierced the veil of dust for the first time. What emerged on the screens was a revelation. Hundreds of massive stars glowing in colors that span the infrared spectrum, filaments of gas stretching across light years, dark pillars where even more stars are forming right now, hidden inside cocoons of collapsing material. This is confirmed by multiple research teams analyzing Webb's data. Sagittarius B2 contains enough gas to form tens of millions of stars like our own. The material is compressed by gravity, squeezed by shock waves from nearby supernovas, and stirred by radiation from already formed massive stars. The result is a factory of stellar creation. New stars ignite in Sagittarius B2 when pockets of gas become dense enough for nuclear fusion to begin. Hydrogen atoms are forced together under immense pressure, fusing into helium and releasing energy. Suddenly, a new point of light appears where only darkness existed before. But these are not small, gentle stars. The conditions near the galactic center favor the birth of giants, stars with 10, 20, even 50 times the mass of our Sun. These massive stars burn through their fuel at a breakneck pace. They live fast and die young, exploding as supernovas that scatter heavy elements into the surrounding gas. Those elements become the raw material for the next generation of stars and planets. There's a direct connection between you and that distant stellar nursery. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged inside massive stars and spread across space when those stars died. Some of that material originated in regions like Sagittarius B2 billions of years ago, drifting outward until it collected into the cloud that eventually became our solar system. In a very real sense, you are made of recycled stardust from ancient cosmic nurseries. The images from Webb show this process in action. Bright red knots mark regions where stars are still gathering mass, pulling in gas from their surroundings. These protostars haven't yet ignited fusion, they are embryos growing in the dark. Around them, older stars have cleared out the gas nearby. Their radiation and stellar winds have blown bubbles in the cloud, creating glowing cavities that reveal the hidden architecture within. Threading through it all, filaments of gas stretch like cosmic highways, funneling material toward the densest regions where star formation peaks. The structure of the cloud is not random, it follows patterns set by gravity, magnetism, and turbulence. Sagittarius B2 is a machine for making stars, and Webb has given us our first clear look inside the engine room. But this nursery is not the only hidden region Webb has exposed. Just a little farther from the center, another surprise awaited astronomers. In a single James Webb image of a region called Sagittarius C, over 500,000 stars appear. Before Webb, this area was almost unknown. Thick dust blocked it from view in visible light. Astronomers suspected something was there, the infrared glow hinted at activity, but the details remained a mystery. Not anymore. The image released by NASA shows a portion of the dense galactic center in unprecedented detail. Stars are packed so tightly they seem to merge into a continuous glow. Dark silhouettes mark where dust blocks even infrared light, and strange features appear that astronomers have never seen before and cannot yet explain. This is where things get mysterious. At the heart of the image lies a cluster of protostars, young stars still forming, still pulling in material from their surroundings. They glow like embers in a fire, their heat revealing their locations even through the surrounding haze. One protostar stands out. It is massive, over 30 times the mass of our Sun, and it is still growing, still accumulating gas and dust at a rate that will eventually make it one of the most luminous objects in this part of the galaxy. Surrounding this growing giant, the image shows something unexpected: large-scale emission from ionized hydrogen, glowing gas that has been stripped of its electrons by intense radiation. This emission typically comes from young, massive stars blasting their surroundings with ultraviolet light. But the extent of this emission surprised the research teams. It covers a much larger area than expected. The source of the radiation is not immediately clear. Something is ionizing the gas across a vast region, and astronomers are still working to identify what. Here's another puzzle. Needle-like structures appear in the ionized hydrogen, thin, elongated features pointing in seemingly random directions. They don't align with any obvious pattern. They don't follow the magnetic field lines astronomers expected to see. These structures might be shaped by outflows from forming stars. They might result from instabilities in the gas, or they might be something entirely new. The team flagged them for further investigation. Every answer raises new questions. Sagittarius A sits only about 300 light-years from the supermassive black hole. The environment is extreme. Radiation levels are high. Gravitational forces are strong. Magnetic fields twist through the region. Forming stars here is different from forming stars in quieter parts of the galaxy. The image suggests more massive stars might form near the galactic center than in the outer regions. The conditions favor giants over dwarfs. If confirmed, this finding would change our understanding of how star populations vary across the Milky Way. Webb gave us the data. Now comes the work of interpretation. And there is much more to interpret. Because the center of the galaxy holds not just young stars being born, but ancient stars that have burned for billions of years. If you look at any spiral galaxy from the side, you'll see a shape like a fried egg, a flat disk spreading outward, a thick bulge rising from the center. Our galaxy has that same structure. The central bulge is a dense ball of stars surrounding the supermassive black hole. Unlike the young, hot stars forming in the nurseries nearby, most stars here are ancient. Some have burned for over 10 billion years. They formed when the universe was young, when the Milky Way itself was still taking shape, when elements heavier than hydrogen and helium were rare. These old stars carry the chemical fingerprints of their era. Astronomers can analyze the light from stars and determine what elements they contain. Stars born in the early universe have fewer heavy elements. Stars born later from gas enriched by previous generations of supernovas have more. The bulge contains both types, a mix of ancient, metal-poor stars and younger, metal-rich ones. This mixture tells the story of how the galaxy grew over time. Here's where James Webb contributes something new. Previous telescopes struggled to study individual stars in the bulge. The crowding is intense. Dust obscures the view. Distinguishing one star from its neighbors required resolution that older instruments couldn't provide. Webb's infrared vision cuts through these obstacles. Astronomers can now measure the properties of individual stars near the galactic center with unprecedented precision. They can sort the population by age and composition. They can map how the bulge assembled over cosmic time. Early results reveal complexity. The bulge did not form all at once. It grew through mergers with smaller galaxies that fell into the Milky Way's gravitational embrace. Each merger added stars with different characteristics. The layers of history are preserved in the stellar population like geological strata in rock. Some theories suggest the bulge of the Milky Way formed rapidly, in a burst of star formation when the universe was less than 2 billion years old. Other ideas propose a slower, more gradual buildup, with stars accumulating over many billions of years as the galaxy merged with smaller companions. The truth seems to be a blend of both, a quick early phase that created the core of the bulge, followed by a long period of mergers and internal evolution that added new layers over time. The bar structure that cuts through the center of the galaxy also played a role, stirring the population and mixing stars from different origins. Understanding the bulge is important because it acts as the gravitational heart of the Milky Way. The pull of those billions of stars influences the orbits of everything farther out. The spiral arms, the disk, the halo, all respond to the mass concentrated at the center. But the bulge is not the only dynamic structure in our galaxy. Surrounding it, spiral arms sweep through the disk, carrying waves of creation and destruction. If you could look down on the Milky Way from above, you'd see a cosmic pinwheel, bright arms spiraling outward from a central bar, lanes of glowing gas and young stars tracing the curves. Dark dust threading between the light. This isn't just a beautiful pattern, it's functional. The spiral arms are where most new stars in the galaxy are born. Gas and dust accumulate in these regions, compressed by density waves that move through the disk. As material piles up, gravity takes over, pockets collapse, temperatures rise, and fusion ignites. New stars blaze to life in the arms, then drift away over millions of years, making room for the next generation. James Webb has observed this process in 19 nearby spiral galaxies, revealing the architecture of star formation at the smallest scales ever seen outside our own Milky Way. The images show filaments of glowing dust tracing the arms like veins in a leaf, bubbles carved by stellar winds and supernovas punctuating the patterns, and bright knots marking regions where dozens or hundreds of stars are forming at once. These findings help us understand our own home. The Milky Way has 4 major spiral arms, 2 prominent, 2 less defined. Our solar system sits in one of the smaller structures, the Orion arm, nestled between the larger Sagittarius and Perseus arms. The arms themselves are not solid structures. Stars and gas pass through them like cars moving through a traffic jam. The arms are actually density waves, regions where material temporarily bunches together before spreading out again. This model is supported by decades of observation and computer simulations. Here's why this matters for life. The compression that triggers star formation also creates the heavy elements necessary for rocky planets. Carbon, oxygen, silicon, iron, all forged in stellar cores and scattered by explosions, are concentrated in the spiral arms. Planets forming in the aftermath inherit a rich supply of elements. Worlds like Earth, with iron cores, silicate mantles, and atmospheres of nitrogen and oxygen, arise from this cosmic enrichment. Webb's observations of other galaxies show that star formation follows predictable patterns in the arms. The youngest, most massive stars appear at the leading edges of the arms, where compression is strongest. Older stars trail behind, having drifted since their formation. This gradient reveals the direction the arms rotate and the timescales involved. Our galaxy displays similar structure, though mapping it from the inside is more challenging than studying face-on spirals from outside. But radio telescopes, infrared surveys, and now Webb's data are gradually filling in the picture. The spiral arms are not static. They breathe, inhaling gas and exhaling stars, pulsing with cycles of creation and destruction. They have been doing so for billions of years, continuously renewing the galaxy even as ancient stars fade. But the disk that holds these arms is not perfectly flat. It bends and warps in ways that puzzled astronomers for decades, and a hidden force may be responsible. If you could see the Milky Way from the outside edge on, you'd notice something odd. The disk is warped. One side tilts upward, the other dips down, resembling a vinyl record left in the sun. This warping was first detected in the 1950s through radio observations of hydrogen gas, but the cause remained a mystery. Several theories competed, perhaps gravitational interactions with satellite galaxies tugged the disk out of shape, or magnetic fields exerted torque on the outer regions, or maybe a long-ago collision left permanent scars. Recent research points to a different culprit: dark matter. The invisible substance that makes up most of the mass in the universe appears to form a halo around the Milky Way. This halo is not perfectly spherical, and not perfectly aligned with the disk. The misalignment creates gravitational torques, like spinning a top on a tilted surface. The tilt pulls on the top, causing it to wobble. Something similar may be happening to our galaxy. The dark matter halo tugs on the disk, warping it over time. This explanation is still a theory, but mounting evidence supports it. Data from the Gaia Space Telescope revealed that stars in the outer disk move in patterns consistent with a warped structure influenced by an asymmetric halo. Computer simulations reproduce the observed shape when they include a tilted dark matter distribution. Here's where it gets even more interesting: the warping is not static. It precesses, meaning the twisted regions rotate around the galaxy like a slow motion wave. The precession period is estimated at hundreds of millions of years. Over time, the warp sweeps through the entire disk, bending different regions as it passes. You are living on a galaxy that wobbles. James Webb contributes to this research by studying the stars in the outer disk with greater precision. Infrared observations reach stars that optical telescopes cannot see, filling gaps in the map of the galactic edge. The more complete the map, the better astronomers can model the dark matter distribution. And here's the truly humbling part: the visible galaxy, all the stars, gas, and dust that telescopes can detect, represents only a small fraction of the total mass. The dark matter halo extends far beyond the disk. Estimates suggest it could reach nearly 2 million light-years in diameter. The part of the Milky Way you can see is like the glowing tip of an iceberg. Most of the mass is invisible, detectable only through its gravitational effects on things we can observe. That invisible mass holds the galaxy together. Without it, the stars would fly apart, the disk would dissolve, and the spiral arms would unwind into chaos. Dark matter is the skeleton on which everything visible hangs, and astronomers are only beginning to understand its shape. You can't see most of the Milky Way. That might sound strange, especially when you look up at the night sky and see that glowing band of light stretching overhead. Stars beyond counting. Clouds of gas illuminated by starlight, the visible machinery of a vast cosmic structure. All of that is just a fraction of what's really there. In fact, all the luminous matter, stars, gas, dust, makes up perhaps 15% of the galaxy's total mass. The rest is dark matter. It doesn't emit or absorb light. It passes through ordinary matter as if it were a ghost. The only way we know it exists is through its gravitational pull, and that pull is immense. The dark matter halo surrounding the Milky Way extends far beyond the visible disk. Current estimates suggest it stretches between 1 and 2 million light-years in diameter. The visible galaxy, spanning roughly 100,000 to 200,000 light-years, sits at the center of this invisible ocean. How do astronomers know this? They measure the speeds of objects at the galaxy's edges: stars, gas clouds, even small satellite galaxies. According to the laws of gravity, objects farther from the center should orbit more slowly, just as planets farther from the sun move more slowly in our solar system. But galaxies don't follow that pattern. The outer regions of the Milky Way move almost as fast as the inner regions. Something must be providing extra gravitational pull at large distances. That something is dark matter. This idea has been tested for nearly a century. Alternative theories have been proposed and mostly ruled out. The evidence from many independent observations points to the same conclusion. There is more matter out there than we can see. James Webb contributes to this research in a unique way. By studying galaxies at various distances and ages, astronomers can track how dark matter halos evolve over cosmic time. Early galaxies appear to have different dark matter distributions than modern ones. Mergers and accretion reshape the halos as galaxies grow. Our own halo carries the scars of past encounters. dwarf galaxies that fell into the Milky Way left behind streams of stars, tracing the orbits of the destroyed satellites and revealing the shape of the dark matter they passed through. Here's something to consider. Right now, dark matter particles are passing through your body. Billions of them every second. They interact so weakly with ordinary matter that you'll never notice. Detectors buried deep underground occasionally register a collision, but the signals are rare and uncertain. The most common substance in the universe remains the most mysterious. We know it has mass. We know it clumps together under gravity. We know it shaped the formation of galaxies and continues to influence their evolution. But we don't know what it is. Solving that mystery would be one of the greatest achievements in science, and the Milky Way is one of the best laboratories for the search. But dark matter isn't the only invisible feature of our galaxy. Even the visible structure hides surprises. The Milky Way is wide 100,000 to 200,000 light-years across, depending on where you draw the boundary. That's so vast that light itself needs a significant fraction of 1,000,000 years to cross it. But here's something most people don't realize: the galaxy is thin compared to its width. The disk of the Milky Way is remarkably flat, only about 1,000 light-years thick in most regions. Some areas are thicker, some thinner, but on average, the ratio of width to height is about 100 to 1. Imagine a dinner plate 200 feet wide and only a couple of inches thick. That's roughly the Milky Way's proportions. Why is it so flat? The answer lies in physics and time. When the galaxy formed billions of years ago, it started as a chaotic cloud of gas. Material fell inward under gravity from all directions. But as the cloud rotated, conservation of angular momentum took over. Material moving in the plane of rotation could settle into stable orbits. Material moving perpendicular to that plane collided with other particles, lost energy, and eventually joined the disk. Over millions of years, the random motions averaged out, and the cloud collapsed into a spinning disk. Stars formed within that disk and inherited its flat geometry. This process is confirmed by observations of galaxy formation throughout the universe. James Webb has captured images of young galaxies still assembling, their shapes irregular and clumpy. As they age, they flatten. Rotation imposes order on chaos. Our galaxy completed this process long ago. The thin disk contains most of the young stars, the spiral arms, and the gas clouds where new stars form. It's the active, dynamic layer of the Milky Way. But there's more to the structure than just the thin disk. A thick disk surrounds it, containing older stars with more random motions. These stars orbit the galactic center, but also bob up and down, passing through the thin disk on eccentric paths. The thick disk formed earlier, before the galaxy fully settled. Its stars carry the memory of a more chaotic era. Beyond the thick disk lies the halo, a sparse sphere of ancient stars and globular clusters. Some of these objects are among the oldest in the universe, forming over 13 billion years ago. They orbit the galaxy on long, looping trajectories that take them far above and below the plane. The architecture of the Milky Way preserves its history in layers. Thin disk, thick disk, halo. Each layer represents a different epoch, a different stage of assembly. Webb helps astronomers study these layers by resolving individual stars at greater distances than ever before. Each star is a data point in the reconstruction of how our galaxy came to be. But one structure cuts across these layers, defying neat categories: a bar of stars and gas that channels material toward the center. The Milky Way is not a simple spiral. At its core, a bar of stars stretches roughly 25,000 light-years from end to end, passing through the galactic core and connecting opposite sides of the inner galaxy. Bars are common in spiral galaxies. About 2/3 of nearby spirals have them. But for a long time, astronomers weren't sure if the Milky Way was among them. Seeing the bar from inside is difficult. Dust obscures the view, and the structure is edge-on from our perspective, making it hard to distinguish from the surrounding bulge. Infrared surveys eventually confirmed the bar's existence. By mapping the distribution of red giant stars, which are bright in infrared, astronomers traced a distinct elongated structure oriented at an angle to our line of sight. The bar was real. James Webb adds new detail to this picture. High-resolution infrared images reveal the stars within the bar region with greater clarity. Measurements of stellar motions show how material flows along the bar and toward the center. The bar at the heart of the Milky Way isn't just a structural oddity, it's a dynamic engine that shapes the galaxy's evolution. It acts as a kind of funnel, channeling gas from the inner disk toward the galactic center. Gas in this region doesn't orbit in perfect circles. The gravitational influence of the bar disturbs those orbits, causing gas to lose angular momentum and spiral inward along the bar's length. This inward flow feeds the supermassive black hole at the core. But not all the gas falls into oblivion. Much of it accumulates in a ring around the center, fueling intense star formation. The star-forming regions of Sagittarius B2 and Sagittarius C, discussed earlier, are both located in this central zone, enriched by material the bar has delivered. The bar also plays a crucial role in shaping the spiral arms. Where the bar ends, the arms begin. The transition zones between bar and arms are sites of complex dynamics as gas switches from bar, following orbits to arm, following orbits. These junctions are hotspots for star formation, triggered by shocks and compressions as material changes course. Even our own position in the Orion arm may have been influenced by the bar's gravitational effects. Over billions of years, the bar has redistributed stars throughout the disk, stirring the galactic pot and leaving its mark on the Milky Way's structure. It's important to realize that bars are not permanent fixtures. Computer simulations suggest they can form, dissolve, and reform over the lifetime of a galaxy. Interactions with satellite galaxies or changes in the distribution of mass can strengthen or weaken the bar. The bar we see today might not have existed a few billion years ago, and it might not survive into the far future. The Milky Way is always changing. The images we see are snapshots of a system in constant motion. The bar channels material, star formation consumes it, and new generations of stars replace the old. The cycle continues, and it has been running for a very long time, perhaps longer than you might expect. The Milky Way is ancient. Some of the stars in the galactic halo formed over 13 billion years ago, igniting when the universe itself was only a few 100 million years old. That means the raw material of our galaxy was already gathering before most other galaxies had finished forming. Before the first planets, before the first heavy elements had been synthesized in significant quantities, these ancient stars were already shining. They contain almost no elements heavier than hydrogen and helium, what astronomers call metals. These metals are forged inside stars and scattered when those stars explode. The earliest generations had no previous explosions to enrich their gas, so they formed from nearly pure primordial material. James Webb has observed some of the earliest galaxies in the universe, pushing back the timeline of cosmic structure formation. What it found surprised everyone. Galaxies existed earlier than models predicted. Structures that should have taken billions of years to assemble appeared within a few 100 million years of the Big Bang. Some of these early galaxies already showed spiral arms. Some contained supermassive black holes. Our Milky Way fits into this picture as one of the early arrivals, not the very first, but close. The galaxy began assembling when the universe was less than 1 billion years old. Over the following 13 billion years, it grew through accretion and mergers, swallowing smaller galaxies and accumulating mass. Recent research has revealed something even more astonishing. Nearly half the matter in the Milky Way may have originated outside it. Gas expelled from distant galaxies drifted through intergalactic space for billions of years before falling into our gravitational embrace. Stars formed elsewhere were captured during mergers. The Milky Way is not a closed system, it's a collector, constantly gathering material from its surroundings. This ongoing assembly continues today. Streams of stars from disrupted dwarf galaxies thread through the halo. Gas falls inward from the surrounding medium. The Magellanic Clouds, our largest satellite galaxies, are slowly being torn apart by tidal forces. In a few billion years, their remnants will merge with us. The age of the Milky Way is not a single number. Different components have different ages. The halo is oldest. The thick disk came next. The thin disk is younger, continuously renewed by star formation. The spiral arms contain the youngest stars of all. You live in a galaxy with parts older than most things in the universe and parts that formed just yesterday. Cosmically speaking, that range of ages, from 13 billion years to mere millions, coexists in one structure, one home, one island in the vast ocean of space. But this island is not standing still. It moves and it carries you with it at speeds that defy everyday experience. Sit very still, feel motionless. But in reality, you are hurtling through space at a speed your mind can barely comprehend. Start with Earth's rotation. If you stand at the equator, the planet's spin carries you eastward at about 1,000 miles per hour. You don't feel it because everything around you moves at the same speed. The air, the buildings, the ground beneath your feet. Now add Earth's orbit around the Sun. Our planet traces an elliptical path roughly 93 million miles in circumference, completing one lap every year. That's about 67,000 miles per hour. Every hour, you travel farther than the circumference of Earth itself. But we're just getting started. Our entire solar system orbits the center of the Milky Way at a much faster pace. The best estimates put this speed at roughly 500,000 miles per hour. Some measurements suggest slightly higher or lower values, but all agree on the general magnitude, 500,000 miles every 60 minutes. At that rate, you travel farther in a single day than most spacecraft have traveled in their entire missions. This motion is called the galactic orbital velocity. The path isn't a perfect circle, it's slightly elliptical, wobbling up and down through the galactic plane as it goes. The orbit takes about 230 million years to complete. One full loop around the galaxy, one galactic year. For perspective, the last time our solar system was in this exact position, dinosaurs were just beginning to appear on Earth. The Atlantic Ocean didn't exist. The continents were joined in a single landmass. Life on our planet was unrecognizably different. The next time we return here, evolution will have transformed everything again. But the movement doesn't stop with our solar system's orbit around the Milky Way. The entire galaxy itself is on the move, traveling through space toward a mysterious region known as the Great Attractor, a gravitational anomaly pulling everything in our cosmic neighborhood. This adds yet another layer to our velocity. And on top of that, the universe itself is expanding, stretching the fabric of space, and carrying galaxies apart from one another. You are layered in motion, spinning on a rotating planet, orbiting a star, circling the galactic center, falling toward distant gravitational wells, and drifting with the expansion of the cosmos. All of this is happening at once, and all of it is invisible to our senses. These motions have shaped the Milky Way's history. Collisions and mergers occurred because galaxies crossed paths. Star formation happened as gas was compressed during these cosmic dances. The structures we see today are the result of billions of years of movement, and that movement will determine the future as well, because another galaxy is coming, and it's coming fast. For a long time, Astronomers believed that spiral galaxies like the Milky Way shouldn't have existed so early in the universe's history. The early cosmos was thought to be too chaotic, too violent, too full of collisions for such delicate structures to survive. But the James Webb Space Telescope has appended that view. Webb has detected spiral galaxies that existed when the universe was only 1 or 2 billion years old. These galaxies, with their organized arms and flat disks, appeared far earlier than any model predicted. One discovery in particular stunned the scientific community: a galaxy nicknamed Andromeda, located about 12 billion light-years away, shows a well-defined spiral structure. It formed when the universe was just a fraction of its current age. Andromeda spans about 32,000 light-years with 2 spiral arms winding smoothly around a central disk. New stars are forming along the arms at a rate dozens of times faster than in the modern Milky Way. This galaxy looks like a younger, smaller version of our own home. The existence of Andromeda and other early spirals challenges fundamental theories about how galaxies form. Standard models predicted that early galaxies would be messy, irregular blobs, chaotic clumps shaped by constant collisions. The gravitational settling needed to form flat disks and spiral arms was supposed to take billions of years. But Andromeda took a shortcut, assembling a spiral structure in less than 2 billion years. The gas settled into a disk, the arms developed, and star formation organized itself along the spiral patterns, all while the universe was still a turbulent fog of merging proto-galaxies. Astronomers are still working to explain how this happened. One possibility involves dark matter halos. If the halo forms quickly enough and has the right shape, it might allow the gas to settle rapidly, providing stability for the disk to form. Another idea is that energy from early supermassive black holes could clear out turbulent gas, letting the remaining material organize more efficiently. Both explanations are still being tested. What does this mean for our own galaxy? The Milky Way's structure might have appeared earlier than we thought. The spiral arms could be older, the disk might have formed faster, and our home may be more ancient in its recognizable form than previous models suggested. Webb is also finding Milky Way twins. At closer distances, over 1,000 disk galaxies have been identified in the early universe, swarming through an era when they supposedly couldn't exist. The exceptions have become the rule. Galaxies like ours are not rare latecomers. They are common throughout cosmic history, emerging quickly and persisting for billions of years. But while some galaxies resemble the Milky Way, one discovery revealed a galaxy that might be a true ancestor. A baby version of our home caught in the act of forming. Imagine looking through a time machine, not at distant stars, but at your own galaxy as it existed billions of years ago. That's what Webb found in a galaxy nicknamed the Firefly Sparkle. It exists about 600 million years after the Big Bang, making it one of the earliest structures ever detected in such detail. But the truly remarkable part is its mass. The Firefly Sparkle weighs about as much as the Milky Way would have at the same stage of development. If you could rewind cosmic time and watch our galaxy forming, it might have looked almost identical to this distant object. This is not just speculation, this is confirmed science, published in the journal Nature. The Firefly Sparkle gleams with 10 distinct star clusters, each visible thanks to gravitational lensing. A massive foreground galaxy cluster bent and magnified the light from Firefly Sparkle, acting like a cosmic telescope that boosted Webb's already extraordinary vision. Without that natural magnification, the galaxy would have been invisible. The star clusters reveal a galaxy in the process of active assembly. Material is falling inward, stars are igniting in bursts, and the structure is chaotic but organized, showing the earliest signs of the disk that will eventually form. What makes this discovery profound is that astronomers have studied the Milky Way for centuries, mapping its stars, measuring its motions, and analyzing its chemistry, but they could never see what it looked like in the beginning. Now, with Webb, they can. The firefly sparkle provides a template, a snapshot of what a Milky Way progenitor actually looked like during the universe's first billion years. The data will help rule out models that can't produce this observed structure. The firefly sparkle isn't alone in its region of space. Webb detected two companion galaxies nearby, one just 6,500 light-years away, the other about 42,000 light-years distant. For context, the modern Milky Way spans 100,000 light-years. All three would fit inside our galaxy with room to spare. These companions might eventually merge with the firefly sparkle, adding their mass to the growing structure. Or they might drift apart, becoming separate galaxies with their own destinies. The future is unwritten, but the past is now visible in ways it never was before. Every galaxy has an origin story. Ours began in conditions similar to what Webb captured in that distant field. A small collection of gas and stars gathering material, forming clusters, slowly building toward the spiral giant we inhabit today. The firefly sparkle is a mirror across time, and looking into that mirror, astronomers are seeing something familiar, something that feels like home. While we gaze at the echoes of our galaxy's past, another cosmic drama is unfolding much closer to home. 2.5 million light-years away, the Andromeda galaxy, also known as Messier 31, looms as the nearest large galaxy to the Milky Way, and the most distant object you can see with the naked eye on a clear, dark night. Andromeda is not just a neighbor, it's on a collision course with us. Andromeda is moving through space at roughly 250,000 miles per hour relative to the Milky Way. That sounds alarmingly fast, but the distances involved are so immense that the approach will take billions of years. For over a century, astronomers have known that Andromeda is getting closer. The light from the galaxy is blue, shifted, meaning its wavelengths are compressed toward the blue end of the spectrum, a telltale sign that it's moving toward us. Every measurement has confirmed the same conclusion: Andromeda is falling in our direction. In 2012, scientists used the Hubble Space Telescope to measure Andromeda's sideways motion with unprecedented accuracy. By tracking the positions of stars over several years and comparing them against distant background galaxies, they could determine the galaxy's trajectory. The results seemed clear: the Milky Way and Andromeda would collide in about 4 billion years. But science is always evolving. A 2025 study using both Hubble and Gaia data added new complexity. Researchers ran hundreds of computer simulations, incorporating the latest measurements of positions, velocities, and masses. The conclusion shifted. Now there's about a 50-50 chance of a direct collision within the next 10 billion years. The certainty faded, and the outcome became less predictable. What changed? Two main factors. First, the Large Magellanic Cloud, a satellite galaxy of the Milky Way, exerts a gravitational pull that slightly alters our galaxy's path, potentially nudging us away from a direct collision. Second, the Triangulum Galaxy, a smaller spiral that accompanies Andromeda, adds further complexity to the gravitational dance. Its presence makes the system harder to predict. Still, one thing is certain: the Milky Way and Andromeda are gravitationally bound. They belong to the same local group of galaxies. Even if they miss on the first pass, they will eventually merge. The question is when, not if. Some simulations show a near miss followed by a long orbital dance before the eventual merger. Others show a direct collision in 4 to 5 billion years. A small percentage suggests the galaxies might pass close enough to distort each other, but remain separate for tens of billions of years. The fate of our galaxy is genuinely uncertain. This might feel unsettling, or it might be a reminder that even on the grandest scales, The universe is full of surprises. Whenever the collision happens, the result will be spectacular. Imagine two cities walking toward each other, millions of buildings, countless streets, infrastructure stretching for miles in every direction. Now imagine them passing through each other, without a single building colliding. That's what happens when galaxies merge. The Milky Way contains between 100 and 400 billion stars. Andromeda contains roughly a trillion. When these two giants finally meet, the total number of stars involved will approach 500 billion. Yet, almost none of them will collide. The reason is distance. Stars are separated by such vast spaces that even in the densest regions, the average spacing between stars is more than 100 billion miles. When the galaxies merge, stars will pass by each other like ships in a vast ocean. Close encounters will be rare, actual collisions almost non-existent. But the galaxies themselves will be transformed, not by impacts but by gravity. As Andromeda and the Milky Way approach, tidal forces will begin to distort both structures. Spiral arms will stretch, disks will warp, and stars will be flung onto new orbits, some even ejected into intergalactic space. The first close pass will trigger chaos. Gas clouds will collide, even though stars will not. When gas meets gas, it compresses, and compression triggers star formation. The sky will blaze with new stars igniting by the millions. Simulations show that during this period, the night sky would look nothing like it does today. Brilliant nebulae would glow across the heavens, and new stars would appear faster than astronomers could catalog them. The familiar band of the Milky Way would distort into unrecognizable shapes. After the first pass, the galaxies will swing apart, but not for long. Gravity will pull them back together. A second pass will follow, then a third. Each encounter will strip away more structure, blend more populations, and erase more of the original identities. Over about 2 billion years, the two spirals will merge into one. The final product will look nothing like either parent. The spiral arms will dissolve, the flat disks will puff into a spherical blob, and the organized rotation will become random motion in all directions. A new type of galaxy will emerge, and it already has a name. Some astronomers call it Milkomeda, a blend of Milky Way and Andromeda. Others suggest different names, but the concept is the same. Billions of years from now, the Milky Way and Andromeda will cease to exist as separate entities. One merged galaxy will take their place. The structure will likely be an elliptical galaxy, a giant spheroid of stars with no spiral arms, no flat disk, and no organized rotation. The graceful pinwheel patterns of both parent galaxies will be gone. This is confirmed by computer simulations run by multiple research teams. Elliptical galaxies are common in the universe, typically forming through mergers of spiral galaxies. The violent gravitational interactions scramble the orderly motions of stars, converting disk rotation into random orbits that fill a three-dimensional volume. Milkomeda will be enormous. The combined stellar population will exceed 1 trillion stars. The merged dark matter halos will create a gravitational well deeper than either parent galaxy possessed alone. Satellite galaxies will continue orbiting the new structure, slowly falling inward over billions of years. Here's a detail that might comfort you: our solar system will probably survive. The chances of another star passing close enough to disrupt planetary orbits are negligible. Earth will continue circling the Sun as it does today. The constellations will look completely different, but our local neighborhood will remain intact. We might even get a better view. During the merger, our solar system could be flung outward from the galactic center. From a more distant vantage point, future observers might see the entire merged galaxy spread across their sky like a glowing dome. Or we might fall inward, closer to the center. The supermassive black holes at the cores of both galaxies will eventually spiral together. When they merge, They will release gravitational waves powerful enough to ripple through space-time across the universe. The combined black hole will anchor the center of Milkomeda, millions of times more massive than any black hole currently in either galaxy. By this time, Earth will be long dead. Our Sun will have exhausted its hydrogen fuel in about 5 billion years, swelling into a red giant and possibly engulfing the inner planets. Even if Earth survives that phase, it will become a frozen rock orbiting a fading white dwarf. No humans will witness the final merger, unless, of course, we find a way to leave. The timeline for the Milky Way and Andromeda's cosmic encounter is so vast that it's almost beyond human comprehension. Yet, even as we look ahead to this distant future, the Milky Way's story is still being written by the smaller galaxies that surround it right now. Our galaxy is not alone in the universe. More than 50 smaller galaxies orbit the Milky Way, bound together by gravity into a sprawling cosmic family. Some of these companions are visible to the naked eye, while others are so faint that only the most sensitive telescopes can detect them. The most famous of these are the Magellanic Clouds. The Large Magellanic Cloud spans about 14,000 light-years and contains roughly 30 billion stars. Its smaller sibling, the Small Magellanic Cloud, is about 7,000 light-years across. Both are visible from the southern hemisphere as fuzzy patches of light, detached from the main band of the Milky Way. But these galaxies are not permanent fixtures. Tidal forces from our galaxy are slowly tearing them apart. Streams of gas and stars trail behind the clouds, stretching across tens of thousands of light-years. This material will eventually be absorbed by the Milky Way, adding to its mass. The process takes hundreds of millions of years, but it is happening right now. Every moment, the Magellanic Clouds lose a little more of themselves to the Milky Way's gravitational pull. James Webb has observed the Magellanic Clouds in unprecedented detail. The telescope detected brown dwarfs, objects too small to sustain hydrogen fusion, in the star cluster NGC 602 within the Small Magellanic Cloud. This marked the first time such faint objects were identified outside our own galaxy. The discovery matters because brown dwarfs reveal information about how stars form. Finding them in a satellite galaxy shows that similar physics operates in different environments. Beyond the Magellanic Clouds, dozens of dwarf galaxies orbit at various distances. The Sagittarius dwarf elliptical galaxy is currently passing through the disk of the Milky Way. It has completed several orbits over billions of years, losing stars with each passage. Streams of its former members now wrap around our galaxy like ribbons. Other companions like the Ursa Minor dwarf and Draco dwarf are ancient systems containing some of the oldest stars known. Their stellar populations formed over 13 billion years ago, preserving chemistry from the early universe. Some satellite galaxies are so faint they were discovered only recently. Ultra-faint dwarfs contain just a few thousand stars spread across regions larger than globular clusters. They are held together by dark matter, with their visible components representing only a tiny fraction of their total mass. These objects challenge our definitions. Where does a galaxy end and a star cluster begin? The distinction blurs at the smallest scales. Astronomers debate classifications, while the objects themselves remain indifferent to human categories. The satellite system preserves the history of galactic assembly. Each dwarf galaxy that fell into the Milky Way left traces. Stellar streams mark their orbits. Chemical signatures identify their former members. The halo of our galaxy is populated by immigrants from consumed satellites. In a sense, the Milky Way is a cosmic cannibal, growing by devouring smaller galaxies. It continues this process today and will keep doing so until something larger swallows us. But there's a mystery in all this cosmic consumption. Something that should be there is missing. Add up everything visible in and around the Milky Way: stars, gas, dust, planets, black holes, neutron stars, white dwarfs, every form of ordinary matter that telescopes can detect. Now compare that total to what should exist based on cosmological models. About half of it is missing. This isn't the dark matter mystery. Dark matter is invisible by nature, detectable only through gravity. The missing matter is ordinary stuff, the same protons and neutrons that make up your body. It should be visible. It should be detectable. But astronomers can't find it. This discrepancy has puzzled researchers for decades. The Standard Model of Cosmology predicts how much ordinary matter the universe contains, based on observations of the cosmic microwave background, the afterglow of the Big Bang. That prediction is precise. Ordinary matter should comprise about 5% of the universe's total energy content. But when astronomers count up the matter in galaxies and gas clouds throughout the cosmos, they fall short by roughly half. Where did it go? One possibility is the hot gas halo surrounding galaxies like the Milky Way. Gas at temperatures of millions of degrees emits X-rays rather than visible light. This hot halo is difficult to observe, requiring specialized telescopes sensitive to high-energy radiation. Recent studies suggest the Milky Way's halo might contain enough hot gas to account for the missing matter. If confirmed, this would mean the visible galaxy is surrounded by an envelope of superheated gas extending hundreds of thousands of light-years. The mass of this halo might equal or exceed the mass of all the stars in the disk. James Webb contributes indirectly to this research. By studying other galaxies in infrared light, astronomers can map the relationship between visible matter and surrounding halos. Patterns observed in external galaxies help constrain models of our own. The missing baryons, as astronomers call them, influence galaxy evolution. Gas that falls into galaxies fuels star formation. Gas that gets heated and expelled removes that fuel. The balance between infall and outflow determines how many stars a galaxy can make. Understanding where the matter went means understanding how galaxies work. Some models suggest the missing matter was blown out of galaxies by supernova explosions and black hole activity. This feedback heated the gas, preventing it from cooling and collapsing into stars. Other models suggest the matter never fell into galaxies at all. It might reside in filaments between galaxies, part of the cosmic web that connects structures across the universe. The Milky Way is a laboratory for testing these ideas. Its halo can be probed in ways that distant galaxies cannot. Absorption lines in the spectra of background quasars reveal gas along the line of sight. X-ray observations map the hot component. Radio telescopes trace cooler clouds. Piece by piece the inventory grows, but the final accounting remains incomplete. Somewhere, vast quantities of ordinary matter hide in forms we have not yet learned to see. The search for the universe's missing matter is just one of the frontiers in our understanding of the Milky Way. Another mystery is even more elusive, a strange glow from the galactic center that might finally reveal the true nature of dark matter. If confirmed, it would be one of the most significant discoveries in modern science. For over a decade, NASA's Fermi Gamma Ray Space Telescope has detected an excess of gamma rays coming from the heart of the Milky Way. This signal forms a roughly spherical halo centered on Sagittarius A, the supermassive black hole. The excess doesn't match any known source. Pulsars, rapidly spinning remnants of dead stars, do produce gamma rays, but models struggle to account for enough pulsars in the right distribution to explain the observed glow. The signal is too smooth, too extended, and too symmetric. One possibility has electrified the physics community: dark matter annihilation. If dark matter consists of particles that can collide and destroy each other, those collisions would release energy, including gamma rays at specific wavelengths, determined by the mass of the particles. The Fermi excess matches predictions for a type of dark matter called YMPs, weakly interacting massive particles. This remains a theory under intense scrutiny. A recent study reanalyzed 15 years of Fermi data using updated models of the Milky Way's structure. The researchers accounted for the galaxy's complex history, including past mergers, that would have shaped the dark matter distribution. Their conclusion made headlines. The gamma-ray signal matches the expected shape of a dark matter halo far better than previous analyses suggested. The flattened, egg-like distribution of the signal corresponds to what simulations predict for a halo shaped by the Milky Way's gravitational history. Still, with current data, dark matter and pulsars remain essentially indistinguishable. But the door is open wider than ever before. If YMPs are real, and if they produce the Fermi excess, then scientists have already detected dark matter indirectly. The invisible substance that holds galaxies together would finally have an observable signature. But confirmation requires more evidence. The Cherenkov telescope array, under construction in Chile and Spain, will scan the galactic center with unprecedented sensitivity. It should detect gamma rays at energies that could distinguish between dark matter and pulsars. Results are expected by the late 2020s. If this theory is correct, it means the dark matter halo is not just a gravitational skeleton. It's an active participant in the galaxy's energy budget. Collisions at the center might inject gamma rays continuously, a slow burn that has lasted billions of years. The galaxy glows in ways we never imagined. Visible light shows stars. Infrared reveals dust and forming stars. Radio waves trace gas. X-rays illuminate hot halos and violent explosions. And gamma rays might finally show us the invisible framework holding everything together. The Milky Way hides secrets in every wavelength. James Webb has revealed many of them, but even Webb cannot see gamma rays. What it can see, however, has transformed our understanding of everything else. Before Webb, astronomers looked at the universe through a kind of cosmic fog. Visible light telescopes showed spectacular images, but dust blocked the view of countless regions. The centers of galaxies remained obscured. Star-forming clouds hid their contents. The earliest epochs of cosmic history faded into darkness. Webb sees through the fog. Infrared light passes through dust that visible light cannot penetrate. Wavelengths that get absorbed and scattered in the visible spectrum sail cleanly through dense clouds. Regions that appeared as black voids now glow with activity. The galactic center is the most dramatic example. For decades, astronomers knew that something extraordinary existed at the heart of the Milky Way. Radio telescopes detected signals. X-ray satellites glimpsed high-energy processes. But visible light images showed only a murky darkness where dust blocked the view. Webb revealed 500,000 stars in a single frame of Sagittarius A. That image alone contained more detailed information about the galactic center than all previous visible light observations combined. Features that astronomers theorized about became directly observable. Structures that existed only in models appeared on screens. The telescope also sees farther back in time than any predecessor. Light from the early universe has been stretched by cosmic expansion. Wavelengths that started as visible or ultraviolet light arrive at Earth as infrared. Webb's instruments are optimized for exactly these wavelengths. Galaxies from the first billion years after the Big Bang now appear in sharp detail. The Firefly sparkle, Alacnanda, and thousands of early structures challenge our theories of how galaxies form. Closer to home, Webb studies planets and moons in our own solar system. Atmospheres reveal their chemistry. Surfaces show their geology. Even objects in the outer reaches, cold and faint, become visible in infrared. But the Milky Way benefits most from Webb's capabilities. Every star-forming region can now be studied in detail. The chemistry of stellar nurseries reveals what elements will become available for planet formation. The distribution of young stars shows how galactic structure influences where new worlds can arise. Webb observed the most massive star-forming cloud in the galaxy. Sagittarius B2 appeared in full glory, its hundreds of massive stars glowing through the dust. Protostars still gathering mass became visible as bright red points at the tips of gas pillars. The telescope also captured the black hole's tantrums. 48 hours of observations revealed the constant flaring from Sagittarius A, activity that previous instruments could only glimpse in brief snapshots. Webb does more than take pretty pictures. It gathers spectra, splitting light into its component wavelengths to reveal chemical composition, temperature, motion, and distance. Every observation generates data that will fuel research for years. The Milky Way we thought we knew was a rough sketch. Webb is filling in the details pixel by pixel, spectrum by spectrum, revelation by revelation. And what those details reveal changes the biggest question of all, the one that keeps people staring at the night sky and wondering. The search for the universe's missing matter is just one of the frontiers in our understanding of the Milky Way. Another mystery is even more elusive, a strange glow from the galactic center that might finally reveal the true nature of dark matter. If confirmed, it would be one of the most significant discoveries in modern science. For over a decade, NASA's Fermi Gamma Ray Space Telescope has detected an excess of gamma rays coming from the heart of the Milky Way. This signal forms a roughly spherical halo centered on Sagittarius A, the supermassive black hole. The excess doesn't match any known source. Pulsars, rapidly spinning remnants of dead stars, do produce gamma rays, but models struggle to account for enough pulsars in the right distribution to explain the observed glow. The signal is too smooth, too extended, and too symmetric. One possibility has electrified the physics community: dark matter annihilation. If dark matter consists of particles that can collide and destroy each other, those collisions would release energy, including gamma rays at specific wavelengths determined by the mass of the particles. The Fermi excess matches predictions for a type of dark matter called YMPs, weakly interacting massive particles. This remains a theory under intense scrutiny. A recent study reanalyzed 15 years of Fermi data using updated models of the Milky Way's structure. The researchers accounted for the galaxy's complex history, including past mergers that would have shaped the dark matter distribution. Their conclusion made headlines: the gamma ray signal matches the expected shape of a dark matter halo far better than previous analyses suggested. The flattened, egg-like distribution of the signal corresponds to what simulations predict for a halo shaped by the Milky Way's gravitational history. Still, with current data, dark matter and pulsars remain essentially indistinguishable. But the door is open wider than ever before. If YMPs are real, and if they produce the Fermi excess, then scientists have already detected dark matter indirectly. The invisible substance that holds galaxies together would finally have an observable signature. But confirmation requires more evidence. The Cherenkov telescope array, under construction in Chile and Spain, will scan the galactic center with unprecedented sensitivity. It should detect gamma rays at energies that could distinguish between dark matter and pulsars. Results are expected by the late 2020s. If this theory is correct, it means the dark matter halo is not just a gravitational skeleton. It's an active participant in the galaxy's energy budget. Collisions at the center might inject gamma rays continuously, a slow burn that has lasted billions of years. The galaxy glows in ways we never imagined. Visible light shows stars. Infrared reveals dust and forming stars. Radio waves trace gas. X-rays illuminate hot halos and violent explosions. and gamma rays might finally show us the invisible framework holding everything together. The Milky Way hides secrets in every wavelength. James Webb has revealed many of them, but even Webb cannot see gamma rays. What it can see, however, has transformed our understanding of everything else. Before Webb, astronomers looked at the universe through a kind of cosmic fog. Visible light telescopes showed spectacular images, but dust blocked the view of countless regions. The centers of galaxies remained obscured. Star-forming clouds hid their contents. The earliest epochs of cosmic history faded into darkness. Webb sees through the fog. Infrared light passes through dust that visible light cannot penetrate. Wavelengths that get absorbed and scattered in the visible spectrum sail cleanly through dense clouds. Regions that appeared as black voids now glow with activity. The galactic center is the most dramatic example. For decades, astronomers knew that something extraordinary existed at the heart of the Milky Way. Radio telescopes detected signals. X-ray satellites glimpsed high-energy processes. But visible light images showed only a murky darkness where dust blocked the view. Webb revealed 500,000 stars in a single frame of Sagittarius A. That image alone contained more detailed information about the galactic center than all previous visible light observations combined. Features that astronomers theorized about became directly observable. Structures that existed only in models appeared on screens. The telescope also sees farther back in time than any predecessor. Light from the early universe has been stretched by cosmic expansion. Wavelengths that started as visible or ultraviolet light arrive at Earth as infrared. Webb's instruments are optimized for exactly these wavelengths. Galaxies from the first billion years after the Big Bang now appear in sharp detail. The firefly sparkle, Andromeda, and thousands of early structures challenge our theories of how galaxies form. Closer to home, Webb studies planets and moons in our own solar system. Atmospheres reveal their chemistry. Surfaces show their geology. Even objects in the outer reaches, cold and faint, become visible in infrared. But the Milky Way benefits most from Webb's capabilities. Every star-forming region can now be studied in detail. The chemistry of stellar nurseries reveals what elements will become available for planet formation. The distribution of young stars shows how galactic structure influences where new worlds can arise. Webb observed the most massive star-forming cloud in the galaxy. Sagittarius B2 appeared in full glory, its hundreds of massive stars glowing through the dust. Protostars still gathering mass became visible as bright red points at the tips of gas pillars. The telescope also captured the black hole's tantrums. 48 hours of observations revealed the constant flaring from Sagittarius A, activity that previous instruments could only glimpse in brief snapshots. Webb does more than take pretty pictures. It gathers spectra, splitting light into its component wavelengths to reveal chemical composition, temperature, motion, and distance. Every observation generates data that will fuel research for years. The Milky Way we thought we knew was a rough sketch. Webb is filling in the details, pixel by pixel, spectrum by spectrum, revelation by revelation. And what those details reveal changes the biggest question of all, the one that keeps people staring at the night sky and wondering,